Assalamu alaikum wa rahmatullah. In this video I will solve some extra exercises. The first one, perform requested conversions. You have numbers from 8 to 7, from 7 to 4, 7 to 9 and so on. We can notice that there is no direct method here, so we have to use the decimal intermediate base. You start from the number written in 8. By polynomial form you get the decimal value, and by a successive division by 7 you get the correct value. The same principle for all variables. Second exercise, write the following decimal as a sum of powers of 10. N equal 1928.765. Here we can write for each digit its weights: 0 for 8, 1, 2, 3, minus 1, minus 2 and minus 3, and you get this formula. What is the quick way to convert a large decimal number into binary? We can use the hexadecimal, and from hexadecimal to binary we use the direct method. So we minimize the number of division operation. We take an example, 9 to 6. We start by the successive division by 16 and we get 39e. And from this value to binary, we use the second table seen in the lesson. Third question, find the base x in the equation 4f16 equal to 142 in base x. Here we use the polynomial form for the two sides and we get a quadratic equation. We solve this equation and we get two solutions, one positive and one negative. We accept only the positive solution because the base are always positive. How to calculate the double, the half of a number, integer or fractional, written in binary? The double of integer is obtained by adding a 0 on the right. We can see in this example 3 in binary is written as 1 1. We add a 0 on the right and we get the double. We add another 0 and we get the double of 6, which is 12. For the fractional number, we move or we shift the point to the right. 3.25 is 11.01. We move this point on the right and we get the double, 1101. The double of 6.5 is 13, so we move the point on the right and we get 1101. And the half is the invert. We move the point on the left. Which numbers have the same representation in all numbering systems? There are two numbers, the 0 and the 1. Among the following numbers, find the number which has a meaning in hexadecimal. Here we have only BAC, ABCD, DE1549C2. For others, there is no H, there is no U, and so on. How to check the parity, even or odd, of a number written in binary, even and odd, عدد زوجي وعدد فردي. We check the LSB, the least significant bit, the first bit on the right. If it's 0, so the number is even, otherwise is odd. How many bits are required to write 614 in binary? We know that the maximum, the largest value in n bits is 2 to n minus 1. So x is less or equal to 2 to n minus 1. We simplify this equation. X plus 1 is less or equal to 2 to n. We introduce log and we get finally n is greater or equal to log x plus 1 divided by log 2. N is an integer. Exercise 3. Suppose a number system of base b. Complete the following conversions. How to write b in base b? We divide. B divided by b is 1 and the remainder is 0, and 1 divided by b is 0 and the remainder is 1, so b is 1 0. B squared is 1 double 0, and b to n, the general rule is 1 and n 0. So if we look for the b to 4, we write 1 and 4 zeros. Let x a decimal number, x equal to 4b25 plus 2b23 plus b plus 7. How to write x in the base b? Here we can imagine this writing as a polynomial form. So x equal 4b25 and plus 0b24 plus 2b23 and plus 0b22 plus b1 b21 plus 7b20. So x is written in polynomial form as 4, 0, 2, 0, 1 and 7. Exercise 1 for the extra exercise in sheet 3. Assume that a computer represents real numbers in 16-bit floating point. The 16 bits are divided as follows: 1 bit for the sign, 5 bits for the biased exponent, and 10 bits for the mantissa. The first question: what is the value of the bias of the shift? The value that we add to get a positive exponent. We know the rule. The bias is equal to n minus 1 minus 1. What is the n here? N is the number of bits to represent the exponent. In our example is 5, so is 2 to 5 minus 1 minus 1. 2 to 4 is 16 minus 1, so the bias is 15. Now the second question: represent the following values in this system: minus 9.25 plus 100.75. We know the steps. The first step is to write the number in binary. So 9.25 is minus 1,001.01 by using the direct binary. The second step is to normalize the writing. Use the scientific notation. Is minus 1.00101 times 2 to 3, y3, because we have shifted the point 3 positions. Now we calculate the biased exponent. You know the relation is BE equal RE plus the bias. Here the bias is 15. 3 plus 15 is 18. So we start by storing the value inside the machine. The sign is negative, so it takes 1. 18 on 5 bits equal to 1, 0010. And the mantissa on 10 bit, the mantissa is 00101, 00101, and all zeros. Now abbreviate the result in hexadecimal. It's very simple. We group each 4 bits and we make the correspondence in hexadecimal. So 1100 is C, 130 is 8, and 1010 is A, and 4 zeros is 0. The same thing for plus 100.75. We start by the binary. Normalize the writing. Is written as 1.1001011 times 2 to 6. Now the biased exponent is 6 plus 15 is 21. We pass to the representation. The sign here is positive, so it takes 0. The value 21 by division is 10101, and the mantissa is 1001011, and we add 2 zeros to get the hexadecimal. Here there is an error, so instead of writing 2, you write 16. You group each 4 bits and you get 5, 6, 4, and C. Exercise 2. Consider the following C++ code. So we have 3 types. Short for integer type in 16 bits in 2's complement. Float is its IEEE 754 SP single precision, and double for double precision. In this program, we have declared 2 variables of short, 2 variables of float, and 1 variable of type double. A receives minus 99, B receives 128, X receives A minus 0.25, Y equal A times B, and Z equal X. Question: express the internal representation of all variables. So we will